My apologies for the delay there. I didn't realize that was going to be an issue. So I want you all to go to page. Whoops. All right. You guys can talk about it on break. Let's get to page 179. In my workbook, it's problem 30.10. I bet this is going to kick in any second now, so I better get over here to pause it. Okay, it says an error occurred. Man, errors just come in droves. All right, well, I'm going to hope this live stream is recording, because if not, I'm out of luck. So if somebody's able to check that, if you're out there in Zoom land and want to see, if you know how to check if it's working on YouTube, that'd be cool. It says it is.
It's working.
All right, I appreciate that. Thank you. All right. Whoa. All right. Let's get charged up. In fact, let's charge up this piece of metal. Ready? Yeah, we did it. Think about it. My claim is I have caused charges to move in this piece of metal. Why? Oops. Can't even hit my hand. So this is a claim I'm making. I claim that when I drop this thing, I get charge separation in this piece of metal. I get a small temporary current. Now watch this. Which way is north? Is it? Nope. The shadow. I think it's pretty much this way. Probably get a lot less. How about this? Almost none. What is the difference here? Whoa, what is going on? This is my claim. Draw a picture here. My claim is that when I drop this rod, and this is 30.10 in your book in theory. Let's say just for a second, we get charge separation. So let's say you drop a piece of metal. My claim is, if you drop this thing, if it's moving down here, V, my claim is you'll get this charge separation. Remind me, what types of charges are free to move in a piece of metal? The electrons. So my claim is, if there was an electron here, what direction was the force on it? If the electrons end up over here, what direction was the force on it? Yeah. So this is my claim. What is the B field that causes that force? The Earth's field. That's why I was talking about north. Well, I don't know if I got the B field the right way, but according to this picture, what direction should the B field be? It's either into or out of the page is the main component we care about. There could be some other components parallel to B, but yeah. Let's just check. If B, let's see, is B into the page? If it is that direction? Let's see. B goes to B. Is that the right direction? Yes, because it's a negative charge.
Oh, God.
Gotcha.
Oh, the old minus charge.
Minus. Do you agree?
Yeah.
All right, so in this case, we see that if I drop this piece of metal and the Earth's magnetic field is going through it this way, I would expect a few of the electrons to get pushed to this end. Now, do you agree eventually this would set up an electric field? What direction would the electric field be? We should get an electric field pointing this way. So what direction is the electric force on the electron? Yeah, opposite. Remember, the force on a negative charge is opposite. So at some point, after I drop this, it's going to reach equilibrium, and there's going to be minuses here and pluses here. So far, so good? Now, but when I have this charge separated, I want you to think of this device, a moving piece of metal in the presence of a magnetic field, as a battery. Please, class, don't get so emotional. No. It depends on the length of the rod, the speed of the rod, and the magnetic field. But just heads up, you're going to see me write this like this. Be perpendicular. So the idea here is the velocity has to be perpendicular to the magnetic field. Or, said another way, the magnetic field, which is perpendicular to the velocity, is what matters. Everybody good on that? Because again, if I was moving this way, V and B would point the same way. There would be no magnetic force, there'd be no separation. So far, so good? Now, earlier in this class, why am I bringing this up? You may recall that E was equal to minus N d phi dt. It turns out this is essentially like an induced voltage as well, right? Dropping. So that's why these are brought together in the same chapter. And what's going to happen here is we're going to get a class of problems where we have what's called a rod on rails. So I've got a visual for this just to show you here. And if you look at 30.11 in your workbook, we'll be doing that in just a minute. So hopefully you can see this. Now, I don't know if you remember, I've got these rails here. These are pieces of metal, right? And then there's magnets hidden inside of here. So we can have a large magnetic field pointing out. The idea is I could connect the two ends of the rails together with some resistance. Pretend this red wire has some resistance here. It's close to zero, but it's not exactly zero, right? And the idea is I can put this rod on the rails. Hey, I just made electricity. Not much, but I did. Think about it. Why? This rod was moving near a magnet. I got emotional with it. Right? So when I do that, this is acting like the battery in the circuit. Isn't that trippy? Oh, yeah. Oh, it's so hot. It's not hot at all. Okay. Is that making any sense? The idea is if I take a rod, put it near a magnetic field, and move it, the component perpendicular to the velocity makes this rod act like a battery. And it depends on the length of the rod. In this case, only the length that's separating the, right? This is the only length that matters here, if I could. Right here, this is the length that matters because that's the length that's exposed to the B field. Out here, it's pretty negligible. All right. What do you think? You ready to try doing some problems with this? Okay, so just keep this in mind. Let's do problem 30.11. Take a second to read it. I'm going to erase the board and get to it. And maybe something I would say, just big picture here, okay? Give me a second before you get too far into this. You're probably going to wonder why we're doing this. This seems super contrived. It turns out the math that we're going to do is used in a lot of branches of science and engineering. Also, the concepts related in this problem matter. So I'll be straight with you. This seems pretty darn silly from a reality standpoint, but there's lots of good physics practice and lots of good math practice. So we're going to do it for those main reasons, okay? All right. What number was this? 30.11? Okay, we got a resistor here. We've got a rod. We got some rails. There's an external B field. That's the magnets inside of there. Right? So this is B external. Now, this particular one, I gave a bunch of numbers because I think sometimes it helps to have some numbers. So I'm going to try and write these down. B external in this problem, I think we said was 500 millitesla. Is that big or small? What's your gut say? Big or small? Huge. Think about the fields you measured in lab. They were 5, maybe 10 Gauss. Gauss, this is Tesla. So the milli is 10 to the minus 3, but this, switching it to Gauss, is 10 to the 4th. Right? So that's like 5,000 Gauss if I did the math right in my head. It's huge. This is, or said another way, do you agree this is half a Tesla? This is like the size magnetic field you use in an MRI. This is huge. Huge. This would be enough to take a vacuum cleaner and suck it into the MRI. All right. So this is crazy big. All right. Just for reference, I like to have a feeling for the numbers. The length was 20 centimeters. What do you not like about that? So you agree it's 0.200 meters? And then I think the resistor was 4 ohms. Anything else we're told? Was the velocity, no? The speed?
The speed 10 meters a second.
Okay, whoops. Anything else that was given, or is that it?
Unknown forces.
Oh, there's an unknown, okay. So again, I want to make clear here. The idea is this scenario right here. I'm the zombie pulling on this thing. So it's not like the rod is magically moving. It's not like the rails are moving. I am a human being pulling on this thing, and that is some force. So I think we're told that force is P, right? So I am the zombie pulling on this thing with force P. To be clear, the rails aren't going anywhere. It's just the rod. And it's like this scenario that I'm showing you where it's pressed up against there. It's not like I'm just moving the rod wherever I want. It's pressed up against there the whole time. All right. All right. What's our first question say? Motional EMF. Okay, so in this case, E motional equals B perpendicular LV. In this case, what is B perpendicular? All of it or some of it? Which way is the rod being pulled? This way, right? The velocity is this way. The magnetic field is this way. What did you say, Christian? All of it or some of it? All of it. Do you agree that the velocity and the B field are perpendicular here? So the B field's out of it. So it would be B perpendicular in this case is, I don't have to think about any sines or cosines. It's just 0.5.
Oh, so
Got it?
I'm thinking about the B field that's perpendicular
To the velocity. We want the
Oh,
B
okay.
field perpendicular to the V. That's what B perp means. Get it? Is that good? Yep. That's why we're doing this. All right. What's the length I want to use? 0.2. And what was the speed? Whoops. What does that spell? 1 volt. I think. Is that what you get when you punch in the numbers real quick? Double check. Yeah. Now notice it's probably going to be useful to keep track of your lowercase v's and your uppercase v's. Lowercase v for this problem is meaning speed. Uppercase means volts. So do something. You can either write out the whole word or whatever you want. All right. Is everybody okay? That's the motional EMF. Zoom, you good?
Yes.
Got it. Part B. What's part B?
Determine the current.
Current. Huh. Got. Yeah, we got delta V equals IR. Rearranging for current, I is equal to. And then, do you agree? We've got this. I'm going to go ahead and use algebra just to get in the habit. B perpendicular L lowercase v divided by resistance. And I think in this problem, what does the current turn out to be? 0.250 amps or 250 milliamps. Okay. So far, so good. Part C is what?
Determine the direction.
Oh, direction. Okay. What do you think? As the rod moves to the right, am I going to get more dots or more X flux? The rod itself moves that way. When the rod moves that way, this is your loop. Do you see it? As the rod moves that way, do I get more dot flux or less dot flux? More dot flux. What is the opposite of adding dots? Adding X's. Since we can't take away dots, we have to add X's. That's our B induced. What direction is the current? Is it this way?
Oh, no, other way.
Is it that way? Yes. Thumb points into the page. Is that helping? No. Thumb out of the page. That would be a dot. Yes. Thumb into the page. That's an X. What direction does current flow in the rod? Up or down? Down. Is everybody cool with that? What do you think? So far, so good? All right. What's next? Oh, so what was that question? What were we supposed to say?
If it's clockwise.
Okay, so what direction was it? I guess that's clockwise, is that right? Okay, D is what? Magnetic force. Does anybody know an equation for the magnetic force? Magnetic
UV
force.
cross B.
It's the magnetic force on what in this case? On the rod, isn't it? Are we supposed to find the magnetic force on the rod?
Wire.
Oh, whoops. That should say rod. Do you agree? I'm thinking of the conducting rod as a wire, and I think I called it a rod and a wire interchangeably. I apologize. So I guess what I'm saying here is I meant this, the rod, okay? Sorry about that. Force magnetic, so that's my fault. Okay, on the rod is what? What would be a good equation for that? I heard IL. It's color coded a little bit. Blue, yeah, that's better. Okay, now I think in this part, we just need the magnitude, right? If I just want the magnitude, in this case, how could we simplify that? I, L, B, sine, and I'm going to say angle like that, just because. All right. In this case, what is the angle? What do you think? What angle are we talking? What? Okay, what was that? Is that you? Oh, who was it? 90s. How do you know it's 90? It's between what and what? Oh, was that you that said it? Oh, I was trying to get somebody else to participate. So hold on. What do you think? It's the angle between the two vectors, right? What direction is the length vector?
Negative J.
Yeah, right there. What direction is the B field?
K. Negative K.
You see it's 90? So what's sine of 90?
1.
Yeah. Cool. All right. Well, at this point, I want to point out, do you agree we in theory know the current?
Yeah.
And we know the length and we know the B external. Do you agree we've got this number? So I'm not gonna plug in the numbers, but you can plug them in and get the values if you want. And you got the solutions if you want to check that number later. Is that good enough for right now on that? What direction is the force? Isn't that part E? What direction is the force? How do we get the direction? Somebody other than Christian. I know he's got it. What's
You just
that?
take the cross product.
Yeah, with a,
Or
Right.
the right hand rule.
so look at the force vector equation. Line up your fingers with what? First vector. Curl them to second vector, thumb points, direction of output. That's a standard cross product right hand rule. Yeah. Is that it? Do I need to flip it? No. I is this way, B is that way, here's this way. We're talking about current, we don't worry about the. So this is the force B. Is that force tending to speed you up or slow you down? It's magnetic braking, right? It's not magnetic make you go faster. So this makes sense. So the direction of the force is in the negative I hat, I guess we could say. Was that part E?
Yep.
What's the last part? Is there any part?
Fourth magnitude of P.
Oh. So now the question is, what's the magnitude of P? P is an unknown, isn't it? How could I figure out P? Huh. Any ideas? I'm trying to learn about a force. What's something we could try? Any problem you ever did in your entire life that had a force in it, what did we always do? FBD. Well, there's a force this way called P. There's a force this way, FB. Which way is it accelerating? It's not accelerating to the right. Yes, it is accelerating to the right. With what value? 0. Right? Look at what's the speed? Doesn't that imply constant speed? If the speed is 10, so that's a trick. You're supposed to realize that it is accelerating to the right, but its acceleration is 0. If the acceleration is 0, what's true about these two numbers? Same magnitude. Got it? What do you think? Feeling good? Zoom heads? What do you think of that?
Good.
Weird? I'm trying to block the glare. Hopefully that was working most of the time. Good enough for right now?
Yep.
All right. Now, we kind of did this problem. I think it's useful to do this again. So look at the next problem. We're going to do it again, but there's going to be a few subtle changes. And I think one of the things students don't realize is what matters and what doesn't. So I want to change it, redo it. It should be pretty fast to redo it, but go for it. Work ahead. I'm going to do it on the board. You can beat me to it. I'll leave this one up. So now we're going, actually, I want to go, I'm going to use the full board. So give me a second. I'm going to kill some of this glare. Let's do that. Probably going to die out soon, so. And you can talk as much as you want, race ahead as much as you want on this problem, okay? I'll catch up. bit. Then I'm going to go back to this one. Downwards, similar. Okay. Okay. We're going to try and keep it algebraic this time. This length is L. This field is B external. Okay, first question. Direction of induced current. Tell me. As the rod falls down, what direction is the current? So it's difficult to kind of think about the current. What is the step that we usually do? We first think about the direction of B induced. So as this rod falls, am I going to try and make dots or X's? Why do you say X's? Let me ask you this. As I fall down, where is the loop? Is it on the top part or is it on the bottom part? It's on the bottom this time. As this falls down, what happens to the dot flux? Do we get more dot flux or less dot flux? Less. So I lost dot flux. I need to put it back. We don't oppose the field. We oppose the change in flux. So if I lose dot flux, the opposite action is make dots. So in this case, B induced is a dot. Does that make sense? And I'm trying to emphasize, you can't just look at the field and know. You have to look at the field and which side of the rectangle forms the loop. That's the key. And this thing is moving downwards, right? That's how I know, right? So I'm losing dots. I got to make them. So now which direction is the current? Is it clockwise or counterclockwise? Counter. This way or whatever that way is. Okay. So what direction is current in the rod? So the induced current is that way in the rod. Got it. And so that's one of the major differences from before. All right, what direction is the force on the rod due to magnetism? Maybe I'll draw it over here. Here's our rod. We know current is flowing this way, right? So that's the current. The B field is out of the page. What direction is the force?
Negative J.
What's the force equation? Remind me. For the full vector force, I L cross B we line up our fingers with which thing first? L or current. Curl it to B plus J hat. It's magnetic braking, not magnetic make you go faster. Does that help, Jacob?
Yeah, I did. I curled from B to L.
So notice it's easy to screw this up. It's on every test. It's probably on every final where I do something like this and test you on it, okay? And so the trick for me is have the equation, I'm staring at the equation in the face, so I make sure I grab the right vector first, then curl to this one, right? And then you really have to watch out, if I do charges, you gotta watch out for the minus sign, you remember that? So that's just, I'm not lying, it's coming probably twice on the midterm 3 and final. All right. What are we supposed to do in this problem? Oh, it's gonna hit terminal velocity. Oh. So the claim is, think about this. Oops. Yeah, that's it. As this rod falls, if these rails are long enough, my claim is, as it falls, do you agree it's going to get faster and faster? As it gets faster, do you agree there's more voltage? BLV. So if you get more voltage, don't you get more current and more magnetic force? My claim is, at some point, the magnetic force should balance what's the force pulling it down. Ah, so the claim is there's a force down on this thing, mg. Which direction should it accelerate initially? Downwards. But the claim is, as it goes faster and faster, you induce more and more current because you change the flux more and more rapidly. And eventually these should balance out. So at terminal velocity, what is the acceleration? Yes. Are you okay with that statement? So now help me out. What's true about these two forces at terminal velocity? Okay, in magnitude, right?
Yep.
This is the other aspect of terminal velocity. How does this help us figure out the terminal velocity? How do I get velocity involved? No.
Make FB into MA and then do dV/dt.
Well, A is 0, FB is,
Oh crap.
where does the velocity show up?
No.
I, matey. Where does the velocity show up?
In the current. of
The current.
WR.
Let's not get emotional. I could just keep saying that all night, and I'm going to. Remember, the current is equal to emotional divided by resistance. You see why I wanted to do this problem a second time? I hope now, seeing it a second time, we're kind of switching the order in which we do things, and maybe now it'll stick. The idea is, how do you get current in these type of rod on rails problems? It's always emotional over R. What was emotional? Do you remind me? Be perpendicular, LV. In this case, is B perpendicular all of it or some of it? It's perpendicular to what? When I say B perpendicular, I mean the amount of B perpendicular to velocity. Are they perpendicular in this case? Yes. So it's all of it. Do you agree? So in this case, I want to emphasize there are cases where that's not true, right? If I angle things, then it might not be true. Okay. All right. So let's plug all this crap in and see what we get. Force B, if I just want the magnitude of force B, what can I write? It's going to be I, L, B, sine theta or something like that. In this case, what's the angle between B and L? That's also 90. It's a different 90, right? Whoops. The idea is B and V make this 90-degree angle. B and current make that 90-degree angle, right? But they're both perpendicular, so that's why I write 90 degrees right here. Okay. equals mg. So now I is gonna be that junk. Look what we get. We're always getting this b squared L squared v. Do you see that? That I is E over R. I'm gonna get b squared L squared v divided by R. Right, because here's a b and an L. So out of all this, I get, sorry, b squared L squared v divided by R equals mg. What are we trying to find here? What was the point of this problem, I guess? Are we supposed to learn about terminal velocity?
Yeah.
Okay, let me ask you something. Is this always true?
No,
No, it's only true when?
sorry.
When the acceleration is zero, which corresponds to what special velocity?
Terminal velocity.
So this equation is only valid if I use terminal velocity. Good? We'll address non-terminal velocity in a minute. Solving for this, what do you get for VT? Mr. G. So cool. Feeling good on that? Mr. G. All right, all right. I think that's pretty good for part C. I think that was part C of the problem. Some of these other parts were probably parts A and B. I don't know what they were. I think it was direction of current and direction of force. So I think this was A, I think this was B, I think that was C. Whatever. Feeling good on that? So now, what would be different if I flip it? To be clear, think about it like this. This problem was like this. The resistor, pretend this red rod or this red wire is the resistor. That was the first case. Is it going to be any different if I do it this way now?
Yes.
Okay, let's see what the differences are. Whoops. Okay, if I flip it, is that right? What do you think is going to happen to the current if you flip it upside down?
Oh, I know being this one.
How can we figure it out? Don't guess. Start over. How did we figure out the direction of current here? Be induced. What's the key to figuring out be induced?
If it's larger or smaller,
Yeah, the flux change. So in this case, if it drops,
it's larger.
we're adding dot flux. So then should I create a B induced X or a B induced dot?
X.
So then, do you think the current flows the opposite way? No, because now the loop is on top. It's a double-double. Whoa! All right. I had a lot of caffeine at some point today, and now I'm like physically exhausted looping. But look at it. X into the page. So doesn't the current still flow the same way? In the rod. Now keep in mind, here, this was counterclockwise. Now it's clockwise, but the loop is flipped upside down.
That's why.
What about the magnetic force? So will that flip? Is this diagram going to be any different? No, it's magnetic braking, not magnetic make you go faster. You see it? I goes to B, goes to up. Cool. Wait, there's more. What if instead of flipping it upside down, I flip the B field? As the rod goes downwards, as the rod goes downwards, I need to first figure out the current, agreed? So in this case, the rod goes downwards, do I need to make X flux or do I need to make X's or dots with the induced? Why do you say dots?
It's getting, the flux is getting, or to me, it's getting smaller.
Okay, so that you just told me you're getting less X flux. What's the opposite of removing X flux? So what do I need to make? X's or dots?
Or
You
dot-
said,
Dot, sorry.
no, it's X.
No, it is.
Yes. Right? If this is falling downwards, I lose X's. Right? That means I need to create X flux. And so the idea is, once again, we see, don't be fooled. Right? Just because the field is into the page doesn't mean induced field couldn't also be into the page. I lost X's. I need to put them back. Which way is current flowing in this loop? Clockwise or counterclockwise? I don't know, but it's that way. Right? So what happens to the current in the rod? What direction is the force on it though? The current flipped, right? So you think the force is, but it's up. Let's see. I goes to B, it's magnetic braking, not magnetic make you go faster. Think about it. The current flipped, but so did the B field, right? In this one, current left, dot. If you flip both of them, right, this is the same as that. Don't you love it? Someone here does. All right, I love this shit. I can't help it. Isn't that fun though? All right, moral of the story, constantly be thinking, what direct do I need to make dots or X's? And that was the purpose. And so I think there's a lot of good right-hand rule practice. There's a little FBD here. All right, and then I'm gonna do one more thing here. I wanna make sure I didn't skip anything. Okay. So we did parts D. I think this was D and I think this was E. Right? So now my question is this. As this thing falls, is it going to speed up at constant rate? Let me ask you something. If I drop this marker, does it speed up at constant rate? Yes and no, right? What happens eventually is air resistance starts to matter, right? A skydiver jumps out of a plane. At first, they get really sick feeling and right, not that I've never skydived, but have any of you? No. Field trip. Let me tell the school they need to come up with this money. We got to understand terminal velocity really well. I'll send an email and see what happens. Oh my gosh, I don't know if I could do it. Why jump out of a perfectly good plane? But the idea is when you jump out of the plane, first you fall like a stone, and then air resistance starts to add up. As you get more and more air resistance, do you speed up at the same rate? No, what happens to your acceleration? Decreases in magnitude, right? Same thing is happening here. I want you to think of mg, that's the force pulling you down. This gets bigger and bigger with time, right? Let's analyze that situation. So at an arbitrary point in time, before you hit terminal velocity, which force should be bigger? The down force or the up force? Down force, right? So mg is going to be big. FB has not quite reached maximum size yet. Which way are you accelerating in this case? Down. All right. What's the force equation for this scenario? Say again.
FB minus mg equals NI.
I would not say that.
That's right.
Right? Coordinate systems matter. You're telling me Usually we think of this as X and this is Y, agreed? By the way, for the rest of this problem, you've got this written up in the notes. I think this is one we should talk and pay attention and maybe not write everything down. I'll explain why when we're done. You're gonna recognize it, and you've got all the notes, so maybe let's just watch, okay, or talk. Or if you like to write, do whatever you gotta do. You can watch the video later. So, all right, that said, usually what I would write is mg minus fb equals ma. By multiplying everything by -1 or flipping the coordinate system so down is positive. So I want to use this one, which means I don't want to write it. I'm going to write it the way I want to write it. Okay. So what I'm going to do is I'm going to flip my coordinate system upside down. Let's say the y direction is downwards. X direction doesn't matter. All right. What direction would the z direction be in this picture? X goes to Y, Z would be into the page, whatever, who cares? Right? So maybe I should have flipped it the other way, but who cares? We don't care. In this case, we see that mg minus fb equals ma. Right? Well, we had an equation for fb. I forget what it was. I think it was, wasn't it b squared? B squared, L squared, V over R, I think. And then I'm just going to use black. I don't care anymore. So my question is, I want to figure out velocity as a function of time. Right? We said that the velocity starts at 0, it's going to speed up. I want to understand the velocity as a function of time. How do you do that? Do you remember? What's that?
Was I on the right track?
I didn't hear you.
Oh, I said RC trans is a joke.
You're probably closer than you think. Yeah, you'll see when we get to the end why you're almost exactly right. Yeah? A differential. Where's the differential hidden in here? Sure thing, eh? A Canadian's favorite differential equation, eh? Now what do I do? Separate and integrate. So let's do this. What's the first thing you might do? I'm going to divide by m. Right? Now, you could do this any way you want. I'm going to multiply by -1 on both sides because I like this term to have a positive sign. So I'm going to say this is b squared L squared V over Mr. minus G equals negative dB. All right. So far, so good. All right. What's next? How do you get the V's with the V's and the T's with the T's? What's that?
You divide V over and then add the GV and then multiply by DT.
Okay, I heard multiply by dt, so I'm going to go with that, the last thing you said, because I like that. And is it okay if I multiply by negative dt? I know it seems silly, you just got to trust me, I know what I'm doing here. Right? I'm going to do that. But wait, is it just times this first term or the whole thing? Oh, we better put these in here. Well, in this case, that gets rid of the minus sign and the dt. I've isolated dv. I'm almost done. What do I have to do next? You can't subtract your way out of this. Divide by the whole thing.
Oh, okay.
Divide by this crap in brackets. What people try and do is add or subtract. It's like, no. Divide by this, right? Because it's a product here. The opposite action is dividing. So let's get that over here. I get negative dt equals dv over b squared L squared v Mr. minus g.
Yep.
All right. Now, you could do whatever you want. I'm gonna do what I want. I want to make, you could do a u sub here, agreed? But why? What I could do is multiply both sides by the same thing and make this v cleaner before I do my u sub, so my u sub is easy. And let me show you what I mean. What if I just take both sides of this equation and I want to get rid of this crap, Mr. b squared L squared. The idea is if I multiply by this in the basement over here, you agree that'll clean this term up? But if I do it there, shouldn't I have to do it here? Mr. b squared L squared. So that's what I want to do. You can do whatever you want. Now, when I do this, I get negative dt all over Mr. b squared L squared equals what's left on this side? V minus Mr. G b squared L squared. So there's a subtle difference. Well, Nick, why is this exactly the same as an RC transient? Remind me, what was the equation you had for an RC transient, Nick?
Isn't it x of t equals x final, or x final plus x initial minus x final, then e to the power of negative 2 over tau.
What is tau in this problem?
You don't see, wait. Oh, it doesn't, wait, doesn't the
That seconds over seconds. Seconds over seconds. Do you see it?
bullshit.
That's tau.
That's bullshit.
Now, checking the units on this is somewhat arduous, but it's true. Okay, we could do it later. It took me like 5 minutes to drag some students through it this morning. I did it. They were not happy and not satisfied. They're like, oh, that's kind of weird. It's extremely uncomfortable to try and get from kilograms and ohms and Tesla squared and meters squared. I can show you later. I don't want to, but I will.
see it. I wanna see it. Oh,
Let's do it later. Just for right now, look at this. V, this is meters per second. This also is meters per second, is it not?
Yeah.
Well, if I'm adding two things, doesn't this also have to be meters per second?
oh,
So this has no units. That means this has no units. That means this has the same units as this. That means this is seconds. That means that's tau. Right. Marker throw. It's been a weird day.
never like to be this.
All right. Oh my gosh. The old marker throw tau trick. I'm tired. All right. But the idea is, Nick, this is the same differential equation. It looks different, but you're going to get this answer. I'll show you if you don't believe me. We're going to do it anyway. You guys want to see it or not?
Yes.
All right. All right. At this point, do you agree the equation is separated?
Yes.
Separate, then integrate. What's a good set of limits for the time integral? 0 to t final? I'm cool with that. Well, what's a good name for the velocity that corresponds to t equals 0? The initial to v final, maybe? That looks good to me. Well, on this, what's true about all this crap? Constant. We get t final all over Mr. b squared L squared. Plugging in the 0 limit, I get nothing, right? Do you agree? And wait, isn't it minus? Negative constant pops out, and then I integrate, I get t. Evaluated at 0 and t final, it's just t final. All right. What's that side gonna give me? I'm sitting on a log. Now, when you do the natural log, it's always log of this. Now you might be saying, wait, don't I need to do a u sub? Okay, fine. Let's say u equals v minus Mr. G over b squared L squared.
This is a problem. This is a Wolfram alpha problem.
What's du? This is constant. What's du? dv. You're saying du dv. Du dv is 1. Du is dv. That means they change at the same rate. This was the reason I moved this crap around. So that my u sub, doesn't this become the integral of du over u? So it's just log of u, and then you back sub. So this becomes you got this in the notes at home, right? You're never going to be able to follow if you're trying to keep up with me here, right? So you got to be right. Well, at this point, man, what could I do? Exponentiate both sides. What happens to the logarithm? Drops. In this case, you see an e to the negative t over tau.
It's fast.
Now my job is done. Okay, everybody gets an A. I just had to wait for somebody to say it out loud. And that was the trick the whole semester. No. Wouldn't that be sweet? You just go until someone gives up. I hate this class. Everyone wins. Squid game 2. All right. I don't know. Let's see. What do we get here? E to the negative t over tau, where tau is Mr. b squared L squared. And then what do you get on the other side? V final minus Mr. G. Are we still good, Zoom? Can you see it? Am I on
Yep,
the-
it's fine.
Thank you. Remind me, you remember what the initial velocity was for this scenario? It was 0, I think, if we release it from rest, right? So you could even plug in the initial goes to 0 right now. If you could have done that hours ago, but whatever. In this case, when I bring that over, look, I get negative Mr. G over b squared L squared times e to the negative t over tau. You see it coming together? Now I'm out of room. I'm gonna pull a little trick here. Oh, yeah. Okay. So now, all that. I move this over. Do you agree it becomes positive? I see that V final is equal to Mr. G over b squared L squared times 1 minus e to the negative t over tau. What is this junk? What is it?
Oh, it's
V terminal. See it? Isn't that it? Oh, V terminal, yeah. Whoa. Isn't this exactly the same as RC transients?
I like shit.
Yeah, Nick, you spoiled it. Thanks, man. Buzzkill. V as a function of time is equal to V terminal, but don't worry, I'll say something for you, Christian.
Why did you say RC transfer?
Okay, this is a lowercase v, not voltage. It's velocity as a function of time, right? So the idea is V final, well, that's the velocity at this time, right? You notice I kind of got lazy and dropped the T final at some point. I think it was right here. What I do at this point is usually at some point I say, well, let's change T final to T. Let's change V final to V as a function of T. What would I do with this all the time to understand it?
Plot it.
Plot it. Oh, what's the plot gonna look like?
Oh, just like.
Asymptotic approach,
Ooh, logarithm.
right? Not logarithm. This, right, logarithm is different.
Oh.
Yeah. Right. It gradually approaches V terminal. Right? Okay. What about the acceleration? How can I get acceleration from this? Well, you spoke up. Do it. What do you get when you take the derivative of this? Right? I could take the derivative. What do you get when you take the derivative of this term? What's the V terminal? That's a constant. That's your max speed. Right? Like people probably know this. The terminal velocity of a skydiver is 90 miles an hour or something like that, right? You guys know this?
People just know that.
Another reason we're gonna go skydiving.
Yeah, there you go.
Okay, we clearly need the funding. Walters, give me the money. All right, we'll see if he's secretly spying on. Walters is the name of the president. You guys know what I'm talking about. President Hancock. All right, give us the money, Walters. We can't learn without skydiving trip. All right, whatever. Yeah, okay, so I forgot. Okay, the first term is a constant.
Okay.
So you're gonna get this term. The minus sign pops out. Do you agree you're gonna get a negative 1 over tau, which cancels this? Isn't that gonna be
Yeah.
A as a function of t equals V terminal over tau times e to the minus t over tau? Can you kind of buy into that? Right, there's a minus sign, there's a 1 over tau, blah, 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 the constant, okay. Does this have the right units? What are the units of e to the blah, blah, blah?
Nothing.
Nothing. This is meters per second. What are the units of tau?
Second.
It's pretty convenient to call this thing a time because it helps us understand it. Huh? What's your acceleration when you first jump out of the airplane? G. Take this and divide it by that. What do you notice is missing? G. It's a G thing. The Mr. B squared L squared drops. It's G. Doesn't that seem reasonable? But if I really want to understand it, what am I going to do? Plot it. Huh. It sure seems to me that we have seen these types of plots and these types of equations about a shitload of times. That's a technical term. These types of equations are going to show up all the time. And that's why I wanted to do this problem the other reason. So the first part was right-hand rule practice. The other part is you really should know this because this is not going to be the last time you see them in an engineering class. Got it? So I feel like you should go through, what part was this in the problem? G. It's G, right? So you should go through part G and make sure you know how to just whip through this because you're going to see it again. That's all I'm saying, okay? Maybe not in this class, maybe not, well, we're probably going to see it in the second half of lecture again.
Yeah.
Can we take a break? I need one.
So what's the drop date again?
Drop right before your talk tomorrow. Your partners love that.
No.
All right. Zoomers, you got any questions on that? I'm telling you, this shows up all the time.
I'm all good.
All right, all right. Okay. Yeah, you can crank it open now. I'll get it.
Don't rely on anything else.
Dropping.
Goodness gracious, that's intense.
Come out of my code, I'm gonna drop the class.
Huh? Aren't you gonna get an A?
Huh?
Are you gonna get an A in this class or a B?
No, yeah, I think
Probably get it, one of those.
I believe I'm on track for a B.
Yeah, so please don't drop. I told you I had a student drop getting an A once, right?
What?
They're like, I just don't feel I understand it enough. I'm like, man, there's a lot of people who would be just desperate to have your grade. Don't you
You are
understand?
desperate to get a C.
What's that?
You are desperate to get a C.
Yeah, I mean, all C means degree. Degree means job. Job means money. That's good. No one cares about your GPA after you transfer anyways.
Hey, Jorsted.
Oh,
I don't know if you want to, but remember to mute the Zoom or whatever, or stop the live stream. for the
yeah,
day.
right on. Yeah, that's kind of nice because then you can tell the halfway point, right?
Yeah.
Yeah, everybody starts out at 100% and it just drops.
Depends on a certain rate.
Just need 5 tau to be longer than the semester. That's it. Okay.
You will never reach zero, because you don't sometimes.
Okay, so at this point, let me see, where are we on this one? There we go. I think it's about time, right? Somewhere close? I don't know, whatever, let's do it. So I gave you a bunch of examples here to work on. You can do them at home. 30.18. That'll get you every time. All right. So I'm gonna let you guys kind of deal with that one. Up until now, we haven't had any angles, and so that's the one where you're constantly having to think about the angles. In the solution, I drew lots of big pictures. Let's see, whatever. There's a couple other ones in here. 30.13 is a classic. It's super good. So, I mean, if you can do 30.13, 30.14, 30.18, and probably 30.16, right? Those are the ones where you'll really see if you're knowing. So let me just write that down. And I put these down there already, but you don't really know what you're doing unless you can do all of these. In particular, if you have trouble with 30.16, you're going to have to do 30.15. So I made some videos for this one, but we'll see talks for 30.17. So, oh, you know what else? I think we did this last time. 19 was the women's NBA problem. Remember that one? So, I mean, I feel like if you can do those, you can handle anything I'm going to throw at you with this. And most of the time when students first start, this scares the crap out of them because it's complicated and disturbing looking. But I want to point out, usually there were 2 boards here. One of the boards took a long time and a lot of math, right? And the other board took not too much time. And usually what happens on a 6-point question, there might be like 4 points on this one and 2 points for all that math. So if you're, most of it is for the conceptual understanding and terminal velocity and stuff like that. Okay, yeah.
Just for this type of problem. Also.
For this rod, these are all rod on rails problems. And again, they're somewhat silly, but I like them because there's a lot of good physics and math in them. So that's why I'm gonna do this to you. Okay. Nobody does this in the right. How often have you seen this on YouTube as something useful, right? Nobody's doing this on purpose. Yeah, all right. Enough said. Next. So I would like to erase this because I'm going to need full boards. All right. I think I gave you all this already, but all right. I want to do a quick review of Nick's favorite topic. RC transients. I want to write down everything we know about RC transients. Why? Because we're going to do something similar right after that. So let's just stick with our basic RC transient. Okay, we had a resistance, we had a capacitance, and we had some battery. Can anybody tell me anything you remember about RC transients? I'm going to say cap fully energized. You might be saying cap fully charged. That's kind of what you were thinking probably, right? Well, if it's fully charged, you agree it has maximum energy as well? Okay, so what were you saying about it? When it's fully energized, what?
That part is pretty short.
Okay. I'm going to say break or open switch or no current. These things are synonymous. Do you agree? When the capacitor filled up, it stopped current flow. Well, let's say the capacitor has 0 energy or 0 charge. What did it act like?
Wire.
Or a closed switch. Some books will say closed switch. Some will say a short circuit. How much current would flow? None or maximum? Okay. That's good. Anybody remember anything else? What did the capacitor preserve? Okay. Now let me write this equation. Do you agree the capacitor equation is Q equals delta V C? Now, humor me, for no good reason, let's take the derivative of both sides. What do you get when you take the derivative of charge?
Current.
Current. Capacitance is not going to change. That's a property of the geometry of the plates. And now I'm going to get a little bit lazy and erase the delta. The idea is the capacitor relates to current using the derivative of the voltage. So sometimes you're going to hear people say the caps preserve voltage. By that I mean voltage on the cap at time t equals 0 plus is same as voltage cap at t equals 0 minus. Do you remember when we drew those 0 whatever pictures? That's what I mean. A capacitor, we say, preserves its voltage. And that's related to this differential equation. You can see it here, right? So it takes time for charge to accrue on the plates, or said another way, it takes time to change the voltage. All right, so you can't instantly change the voltage of a capacitor. What was the time constant? Tau was equal to RC. Now, we recall there were two types of plots. I'm just going to call this X because X could be voltage or charge or things like that, right? I would call this exponential decay. How long did it take? 5 tau, approximately. That was 99.6% done, or something like that. I'm not sure on this sig fig. Right? Well, let's just do it real quick. E to the -5. Can somebody type in E minus 5 and then 1 minus E minus 5, or 1 minus E to the -5? Or something like that. 1 minus E to the -5. Oh, it's 99.3. Sorry about that. I'm a bad person. Okay, something like that. Okay. This was exponential decay. This looked like the equation. That was the result we found for exponential decay. And X max is right here, right? The other one was asymptotic rise, is what I'm going to call it. It's not logarithmic. And somebody else might have a different name for this. What was the equation for this one? And I wish it could have been easier when we were learning it the first time, but I feel like this is what I'm hoping you understand from all your work before. And to be clear, we said that X could be charge, voltage, or current, but not U, not P. Good? There's a new thing in town. That new thing is called inductance. Well, let me pause. Any questions about all this? I feel like that's a full summary of RC transients. Man, if somebody takes a picture of that and sends it to me, maybe I should type that up for you and give that out to my future students for the RC. You know what I'm saying? Because I'll forget what all we said. Would that have helped you guys on the test?
Yeah.
Probably. So I should at least type that up and make it a handout or something. And I don't know why this never occurred to me till this moment, but whatever, right? You just do better every year a little bit. Yes?
Did you talk about they can use energy or?
Yeah.
So X.
X can be Q, delta V, or I, but it can't be P or U. No PU. That's a lot. All right? Okay. Well, now I want to talk about something new. And it's related to this topic, so I want to leave that board untouched. So let's go over here. You agree there's an equation that says induced EMF is something like minus N ddt of B times A, and let's say cosine of some angle. That's our induced EMF formula. Now, I just wanted to, oops, oh, it's crashing. This is our induced EMF. I'm going to make a one loop circuit. I'm going to have a switch here. My claim is that when I close this circuit, will current flow?
Yes.
Yes. If you close the circuit, which direction should current flow? Clockwise or counterclockwise? All right. Will that create a magnetic flux through the loop? Which way? Did the magnetic flux change? It went from nothing to something, right? Because before it looked like this. No flux to a dot. Will the act of closing this circuit induce a current?
Yeah.
Which way? So you just told me we're going to induce a current this way to try and cancel that. The act of turning on a circuit causes that circuit to oppose itself. You already know this. The act of turning on your motor caused it to act like a generator, which opposed itself. And that's what determined the ultimate speed of the motors. Back EMF. Okay, now I'm going to do some serious hand waving here. We'll even throw jazz hands in there. My claim is that here, somehow, this is proportional to I. This current, right? My claim is that this B field that you put through the loop is somehow going to relate to the current, right? Let me just say it this way, because I don't like having those extra symbols in case it doesn't show up. Do you agree that this B field that's going to cause the induced EMF should relate to the current? So my claim is that there's going to be an induced voltage which is equal to some constant times di dt. That is my claim. Now think about this. The area of the loop is not going to be changing. Right? Mu naught is not going to be changing. That's a constant. So that my claim is that there's a bunch of constants in here. N's, I's, maybe there's a minus sign in here. It's almost as if the voltage on an inductor, a new piece of equipment we haven't discussed yet, is equal to L DI dt. And there may or may not be a minus sign here. I don't want to care about that. So let's just throw on an absolute value here. There's a new thing in town. L is called inductance. Inductance has units of henries.
Damn.
Okay, we're on Zoom.
Oh, it's not even like, I thought it was.
Henries. Yeah. All right. So the idea here is there's some property here that relates to the current change, and I'm going to call that property inductance. Now, sometimes you'll hear this called self-inductance because it's the ability of a circuit to oppose changes to itself. Right? Isn't this weird? Now, okay. So far, so good. Does this equation look familiar at all?
For sure, figure out this equation. Really just figure it out. I'm a genius. I don't know any variables.
See it? It's a companion to this one. Similar, but not the same. We see that the current is capacitance times dV/dt. Voltage is inductance times dI/dt. They're mirrors. Capacitors preserve voltage. What do inductors preserve? Current. Think about it. Coils of wire oppose change in flux. That means they oppose changes to their current, because if you change the current, you change the flux. Crazy. So what I'd like to do is write down RL transients, but I need the whole board to do it. So I'm going to have to kind of erase some of this and save this one piece and this piece. So before I erase this, any questions on that? Good? All right. So, and then you're going to be like, oh, I know this already. So I know I'm hard on you, especially at the beginning of the semester, but I'm hoping you're going to get a little tiny bit of a reward here where you're like, oh, this almost makes sense. Okay. Let's summarize RL transients. L is inductance. Units of henries. We know that the voltage on an inductor I'm just going to stick it as the value so I don't have to worry about that. Is L di dt. Tell me what inductors preserve. Yes. Whatever's in that derivative is in there. Take a look on your equation sheet. You see these equations somewhere? Look for them. They're right. Here's one. There it is. See these two right there? So the idea is, this is my way of saying capacitors preserve voltage. And this is my way of saying induct. Oh, and so you see there is a minus sign on there. Okay, and that came from the induced EMF equation. So now I can just put this minus sign in, right? So the idea is, that's cool. The faster you try to change the current, the more the inductor spikes up the voltage and says, whoa, hey, let's chill out. Let's keep things the same. All right. Well, let's check the units of this equation. I want to check the units of this equation. Volts equal. All right, let's focus here. Henries times amps per second. Do you agree? Yeah. Volts, henries, amps per second. Huh. Why do you think I would want to check the units? No. Solve this for seconds. Seconds is equal to henries times amps over volts. What's an amp over a volt? I don't know. Give me any equation that relates amps and volts really quick. V equals IR. Huh. So what's, I guess,
Hey,
amps?
Jorstad.
Yep.
Sorry, that's you're off the screen right now.
Oh, thank you, thank you, thank you. Forgot, thank you. Sorry about that. Appreciate the reminder. Really appreciate that. Okay, so let's solve this one. Volts equals IR. So let's see, we need amps over volts. So I need to solve it this way. 1 over R is I over V. So you're telling me that seconds is equivalent to henries per ohms. Why would I be bringing that up? Tau. What is tau? L over R. That's written on your equation sheet. So the whole point of this unit analysis was just to give us an idea what tau is. Cool with that? So we can see that inductance over resistance. So it's similar to RC, but there's a few little changes. All right. So I'm just going to summarize this way. Just so I have enough room. Flipping all this around, somehow this miraculously showed us that seconds was equal to henries over ohms, which told us the time constant. Okay. Okay, what's something else I can talk about over here? How about inductor fully energized? If you had to guess, if it's fully, what type of energy does a capacitor have? Capacitors.
Oh.
Electric fields are in capacitors, electric energy. Inductors have to do with magnetic energy. Cool with that? All right. So when we say an inductor is fully energized, that means it has maximum magnetic energy. If it has maximum magnetic energy, do you think it has a lot of current or no current? A lot. So when it's fully energized, it acts like a short. Max current. What was the other way we called it? Closed switch. This is a little different than a capacitor, isn't it? So inductors oppose changes. So when you first turn it on, that's when it has trouble. And then it says, oh, things aren't changing that fast. I'll chill out. Okay. So take a guess, if the inductor has no energy, open switch, no current, break. It's a broken circuit. So sort of like we saw resistor and capacitor rules are flip-flopped, inductor and capacitor rules are flip-flopped a little bit. So when an inductor is fully energized, that's when an inductor acts like a short. When it has zero energy, that's when it acts like a break. So far, so good. I had a simulation to show you. It was working this morning a few hours ago, and now it's not. I can't figure it out. I wish I could have shown it to you. I can't. All right. But I can have you prove this to yourself later. My claim is this. Inductors really like to preserve their current, really like to preserve their current. If you don't know what the symbol is, I should show you the symbol. This is the symbol. It's like a curly looking line instead of a jagged spiky line. So inductors have this symbol, by the way. What is something that you think has large inductance? What are things that might have large inductance? We need things that produce large B fields. Solenoids are the classic example. Do you see how this looks like a solenoid? If you don't know what a solenoid is, Jesse's going to show you tomorrow in class, right? But a solenoid is just basically lots of windings. I think we saw those in here too, yeah. So, okay, so we know what a solenoid is. What type, so basically lots of coils. What are objects in the real world that have lots of coils?
MRI, AC.
That you have at your house maybe? What's that? A vacuum. Anything with a big motor in it. A fan, right? Fans have a big motor in it. They have lots of coils in it. Try this. Don't try this at home because we're on Zoom, right? Don't try this at home. Just in case somebody's watching, right? I don't want to somehow get sued for this, but you see this. Have you ever pulled the plug on a vacuum while it's running? Vacuums have a huge motor in them. What do you see when you pull the plug on a vacuum when it's running? A spark. That's the inductor trying to keep the current flowing even after you pull the circuit out of the wall. That's what inductance is. So that's dangerous. We don't want to do that in general. So a lot of times circuits will be designed with things called flyback diodes, and you don't have to understand this. We'll discuss it maybe a little later. It's in one of the questions in the workbook, but you can do tricks to kind of avoid these kinds of sparks. You can create a path inside your device so that if it's accidentally turned off, you don't accidentally have a huge current spike. This is a big deal in certain applications in physics. Let's leave it at that. So yes, inductors like to preserve their current so much that if you have a huge one, like a motor, when you pull the plug, you'll see a spark. That's how much they like to preserve it. Is there anything else over there? That doesn't change. So let me go over here again. Oops. That stuff is the same. This would be different, wouldn't it? This is the only other piece we have to talk about. But these equations still work. Turns out we don't have to worry about charge anymore. It's basically only going to be V's and I's. All right. All right. And then if you need power or energy, we can figure that out. There's equations on the back. So maybe there's some other equations we should see here. Maybe I'll allude to this really quick. I'm just going to pull them off the back so I don't forget. The magnetic energy is 1/2 L/I squared. All right, and then is there one other? It turns out if you care, inductance. Did I go off the board again or am I not? Whoops, sorry. Shit. Magnetic energy is that. And then there's a definition, I think it's magnetic flux. What is it per unit current? Yeah. Is that it? Thank you. So if you really had to figure out, this is sort of like the equivalent of, you remember C was charge per unit volt? There's a little bit of similarity. Capacitance was charge per unit volt. Inductance is flux per unit current. Something like that. This is somewhere on there. I don't know where it's in there. There it is. Right there. Kind of near the middle box. What else did I want to say? Anything else on there? Just so I have it all on one board. I think that's most of it. Oh, there was this comment here. So current through the inductor at time t equals 0 plus is same as I through the inductor at t equals 0 minus. Right? Again, one way to think about this is the vacuum cleaner is at full speed. The current is running, right? And so you pull the plug, that's like closing the switch. It's like, man, no, I'm going to keep the current flowing even though you pulled the circuit out of the wall, right? It preserves that current as you change the switch. Crazy, right? That, I think, is all of it. Any questions while it's up there, or should we do a problem? Time is it? Okay,
A little less than 35.
okay, got it. Let's do a problem, right? I just shut my book. I don't know the problems. Questions from Zoom? Any Zoom questions?
I grabbed a screenshot of the RC thing. Do you want me to get one of that too?
Yeah, sure, why not? I'll do that. I'll dump it together. I'll just make one big page and I'll hand it out to students that first day, and then I'll say, hey, don't read the bottom of the page. And then
Right, I got it.
I'll dump it in the book for future. Thanks, boss. Okay, we're gonna do, let's try, I'm gonna show you something. Let's do 30.23. 30.23, all right? Let's go over to this board. .23. Kind of cool, right? Do you feel like you already understand RL transients? I bet you do.
Sorry, Nick, get up there and show me.
Of course, I also think my tests are easy. So that tells you how much I know. Like, oh, these tests are too easy.
Yeah, we'll be able to get the right answer by March.
I've learned that one over the years. Even when I think the test is way too easy, it never is, right? It's, of course, it's easy for somebody that's been doing it 20 years, right? It's not easy if it's your first semester. I know that now. I used to expect people to only do 3 times as slow as me. And they were always running out of time. 4 times is tough, right?
Yeah.
You on your ratio now?
Yeah, now I try to keep it to 4 to 1 as opposed to 3 to 1.
We have 3 to 1, about 4.
No, that was 4 to 1.
Oh, well.
Yeah, yeah.
It's losing for-
It's always 4 to 1.
Yeah.
I don't
You
know.
guys are just slow. Yeah, and again, you should be slow because you're learning, right? So don't take offense at that, but you are slow. Fine. You know what? I need to make this skinnier if I'm gonna fit this on. I apologize. I just remember we're gonna need 0 infinity plus picture crap. So my apologies, I gotta redo it. This is L, this is R. And wait, isn't this 3R?
Yeah.
Hey, Jacob, do you happen to know in the YouTube video what minute mark we're at right now?
I'll look right now. 1 second.
I appreciate it. That might help me because I'll put a comment in there because everybody's gonna want to see this later. Appreciate it. I'll put it in the comment on the YouTube to help people skip right to it. They'll save me searching for it.
I think I have to wait until after class because
Okay,
it
let's
doesn't
not-
show
I'll
up.
find it. It's not your fault, or it's not your responsibility. I'll take care of it. Thanks for, I didn't know if that was something easy. Thanks for checking. It's probably about, yeah, okay, 10 minutes before the end, 20 minutes before the end. All right. Oh, shoot. We're closing the switch, aren't we? Sorry about that. Too busy thinking about YouTube. Hey, I'm a RL transient influencer. Funny, nobody gets influenced by them. I wonder why. Okay, this is t equals 0 plus and t equals infinity, right? Okay. There's only one thing we care about in the 0 minus picture. What is it? Current where? For the inductor, right? Now, in this case, do you agree current is 0? And do you agree current through the inductor is current in everything? All right, cool. So why do I care about that? That's what carries over. Inductor preserves its current. Boom. The rest of the problem is off to the races. Well, let me ask you. Where would you go from here? If I want to analyze everything in the circuit, I need to understand, oh, and the battery has size E, sorry about that. Okay, in this case, what would you analyze next? If I know the current is 0 to the inductor, would you try, what else do we know? I need to know all the voltages and all the currents. Do I know
The
the current?
voltage of the inductor 0 then?
I don't want to go that way. I think it's easier to talk about this one. Do you know the current is 0? Yes. So what's the current in the resistor? 0. Same pipe. Agreed? Now, Jacob, it turns out what you thought was completely wrong. And I'll show you why. What's the voltage on this resistor and why? 0. Why? V equals IR. So if the voltage across the resistor is 0, what voltage must be across the inductor? How do you know it's E? Yeah, I was gonna say KVL, but you guys, yeah, I think what you're saying is all similar. Do you agree that when you go around the loop, if this has no voltage and this has E, something over here better take up that E volts? Well, if there's none on here, Jacob, are you clear why that's not 0, but actually E?
Yeah, I see that.
Now, you may be thinking about the polarity of this. Remember that there was a minus sign somewhere? I'm just going to show you the polarity here on this one case. Okay, do you agree the upper terminal like that? Well, in this case, in order for this to be 0, wouldn't the polarity have to match over here? And the idea is, think about this. If you're doing KVL, let's say this is ground, so that's 0 volts. When I come up to here, what's the voltage? What's the voltage? What's the voltage? Okay, let's go this way. What's the voltage? What's the voltage? See how they're both E? See that? So that's like, right, there's nothing here, and I know that the resistor with no current has no change. So if I have no change in voltage, if this is 0, this is also 0. Well, going this way, this is 0 to E. This must also be 0 to E. Clear on that? All right. Okay. After a long time, inductor fully energized in this scenario, right? After a long time, the inductor is fully energized. What do we know? Okay, I want to think of acts like a, yes, L acts like a short. That's the term you're going to hear. And you had also said it correctly. If this is a short circuit, what's the current? If it's a short, do you agree it's basically like a closed switch? So what's the current?
Maximum?
What is the maximum in this case? Right? If it's a short circuit, do you agree this is the only thing in the circuit worth caring about? So now, couldn't I tell myself the voltage across the resistor? What's that? E. Now, wait a minute. Don't we know an equation for a delta V across the inductor? After a long time, are things changing or not changing after a really long time? Not changing. So what's di dt? Makes sense. So the current through the inductor is 0, right? No! These are in series. We are. You're tired. Okay, got it? if I wanted to solve for the current as a function of time, it's going to be I final plus, Nick, you remember it. So you yawn, I gotta,
Initial and then the rest of the garbage.
what's tau in this problem? No. Aha! The old L over 3R. So dumb, man. Okay, in this case, what's I initial? 0. What's the name of my dog? 0.
You have a dog named Zero?
I unfortunately do. I do not like dogs, but it came with the package deal. It was worth it. Hey, Juanita. All right. She's never watching this. She has to listen to me. You guys are done in one semester. She's got like her whole life listening to me. I feel sorry for her. All right, whatever. What's E final? Isn't that E over 3R? Let's get this damn problem over with. There we go. Oops, that E looks terrible.
Hey, no way. That's not possible.
There we go. What do you think? Now that I tell you this, do you feel like you can do it?
Practice.
What if I wanted the power delivered to the resistor? What is it? I squared R. You just shove in this ugly equation and don't try to think too much. Just leave it as, well, wouldn't that be E squared? Wait, I'm wrong.
Oh, it's B.
No,
Oh.
it's 3R. The power delivered to a resistor of size 3R is I squared times 3R. Bad, 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 Rob. Okay, we get E squared over 3R because one of the 3R squareds cancels with this 3R. And then I'm going to get this stupid thing squared. Just write stupid thing squared. Don't overthink it. What do you think? Could you solve for time?
Yeah.
Right? Let's say I show you a plot of the power versus time, and I say solve for t. You pick a point somewhere in the middle, right? And then you say, okay, I know p, I know t. Do some work, take a square root, do a logarithm, blah, 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 blah. Ready for a fun puzzle?
Yes.
Let me see. Ooh, I'm ready for a delicious problem. Are you? Look at 30.25. I need a delicious problem. Well, 30.25 says it's delicious. I tell you what, one thing I can tell you is never write a book, people. I don't care what kind of book. It's a lot of work. And then you go crazy and start saying things like delicious problem or zombies or whatever, right? You'll go kind of crazy. Speaking of zombies, I started watching this movie, what was it? Army of Thieves. I thought it was going to be like a jewel thief movie, and then I'm not going to say anymore. It was kind of like, what? I had no idea.
Was it good?
Well, I watched the whole thing, but I watch a lot of movies, so that's not a good judge. And I mean, you see how I dress. I don't necessarily have good taste. So, yeah, I would recommend it, but I also like Train to Busan.
Have you seen Army of the Dead?
I haven't, so I realized that's related. I didn't know that. So maybe I'll watch that now. All right. Let's look at 30.25 real quick. I know it's time to go, but trust me.
It's not your step up, we don't go over time.
Yeah, right? It's just because I love physics so much. I actually do. I don't know why.
I like violin.
So I'm going to warn you, inductors, there's a reason we cover magnetism second, and there's a reason we cover RL transients after RC. It's not quite the same. You probably have an artificially inflated sense of how good you are at this moment. Shocking, right? Okay. Let's say, let me ask you this. Let's start with switch closed. Okay? And we're gonna say this is steady state. Have you seen the word steady state before? I think we've said it. Or closed long time, that's the other, the steady state just means closed long time. Help me out. If this is closed for a long time, what does the inductor look like? Short. So do you agree it's equivalent to this circuit?
Yes. Probably.
Right, the L disappears. I have an R and a 9R. Okay. Just help me out. I don't need the total current. I just want to know the current in this branch. Because it's not like every current is preserved. It's just the current in the inductor. So what's the current through this branch? Do I need to do the R equivalent? Yes or no?
No.
No. Do you agree if I look at the node voltage? This is 0, this is E, this is E, this is E, this is 0, this is 0. What's delta V across this resistor? E. What's the current? E over R. Now, this is getting, I am tingly. This is exciting. Watch what happens. I know we're going late, but I think it's worth it. Of course, I have a strange perception of what is fun. Let's open the switch. What? This guy sounds crazy. What's his name? Now, you know what? I'm going to do one more thing. Do you agree the current in this one is E over 9R? Right? Well, just watch what happens. When you open the switch, something changes. Agreed? What does the inductor preserve?
Current.
So what is the current through the inductor?
Zero. No.
What does the inductor preserve? What was it? Is E over R? It's E over R. It's E over R. That's what we got to lock in, right? Okay. What's the voltage across the inductor? Now wait. Why take the derivative? But we don't, right? That's not going to help you in this picture because we don't know how it's changing. We just know its value. Look at this. What's the velocity at max height? What's the acceleration at max height? Negative G. Is the derivative of 0 negative G? You don't see it, right? But it's true. It's because the value at one point cannot tell you the derivative at that point. All right? Now, is this a series circuit? Yeah. So what's the current here? Which way? Who dominates this circuit? Who's in control? The inductor. The inductor rules this land. So in this case, the inductor's current cannot change. If the inductor's current cannot change, that's the current in the loop. So what's the voltage on this puppy? What's the current on this?
That's crazy.
What's the voltage? What's the voltage across the inductor? Who is the source? Who is acting as the power source in the circuit now? Who has the energy? So what is the voltage across this? KVL. This is like the battery. 10 E. You get 10 times the voltage. Weird, right? This extreme spike in voltage is what allows the current to flow through air when you unplug the vacuum cleaner. So what you can do is put a diode in the circuit like this. Diodes only allow current one way. This is called a flyback diode. So this gives it a path. So instead of sparking, it'll go right through there. Now I think we're over, but hey, check out the next one too. I know this is going to blow your mind. I know it's tiring. The limitations of the model are 30.26. What if you have two inductors? Too hard for us. So the weird part about that one is, if you have two inductors, one in each branch, which one would win? They both win, and then you use a superposition principle to say this current persists. So does this current. But if they both persist, they cancel each other out, and you get no current. What? Inductors! I'm telling you, it's a little weird, but that's pushing the limits. That would not be on a test, but I feel like you could learn a lot from that. It'll blow your mind. I appreciate the extra minutes. I need to get a remote for that clock to like slow down the motor.
Oh, that'd be a good way to mess with your.
That's right.
Classes of
So how can I slow down the motor? I can put a large oscillating solenoid with a large magnetic field to change the DC motor and get a back EMF. Why is that large solenoid next to the clock? I have a strange perception. of time. Hey, study hard, practice hard. Next week you get a break. Hey, please remember, have more than one mode to bring your talk. Like save it on Google Drives and bring a flash drive just in case for your talks tomorrow. We'll do a lottery when you get there to see who goes first. I'm excited. It's going to be fun. We'll learn something. All right.
Get away from the phone like by the clock by just putting random shit on the wall.
All good?
Oh, yeah, I had a question.
Yeah.
For the percent difference, should we do the absolute value? or-
Sure.
But I was gonna ask, what does a negative percent difference?
Negative means, I gotta write it down so I can see here. Let me see. So percent difference is
Take it easy, I'll see
experiment minus theory over theory. So if you get negative numbers, that just means your experimental results were smaller than your theory.
Yeah.
Yeah. If you get a positive, that means, so like if you had dots like this,
Mhm.
that means your experiment was less than the theory.
Okay.
Cool.
Yeah,
And you could leave, if they're all negative, you can leave it negative. But if they're kind of like random, where it's like some are above and some are below, then I would maybe test the value, because when you average them, that would be artificially low.
okay, yeah, because, I took an average.
Yeah.
And they took it on negative, but-
I was talking to a chemistry instructor. Sometimes what the chemistry instructor said he used to do, what he would be plotting the percent difference. Versus, so he'd get the percent difference of this and this, like in a column,
Yeah.
and then he just plot it.
Uh,
And that way you could say, oh, notice points near the end have a positive percent difference, points near the middle have a positive, but these two regions have negative.
Okay.
But you don't have to do that.
Yeah.
That's what he said he had to do when he was in grad school.
Yeah.
Yeah, cool.
Yeah, I thought it was just more
Yeah,
in depth.
well,
I didn't know.
I'm more
far
interested
you
in you guys getting speaking experience than, yeah.
I
Yeah,
remember for young blood, he just told me to take the absolute value.
yeah, exactly. So, because we're gonna look at the plot.
Yeah.
Yeah, but if they're all negative, you can keep it negative or something.
Okay.
Okay, cool?
Yeah.
Yeah. I wish we had more time to do error analysis, but I think the speaking skills matter. What's your major?
Civil engineering.
Yeah, so your ability to communicate is probably much more important than your ability to do detailed error analysis calculations. That's my passion.
Yeah.
You will see that probably later in a branch called when you have to deal with tolerances, but that's again more for mechanicals.
Yeah.
So I don't know enough to really be educated, so let's leave it at that.
Okay.
You can get out of here. Is that good?
Yeah. Okay.
Yep. All right, you got your phone, right? All right, you got it. Cool. Nick, question?
Wants those units.
Oh, you want to see the units? Okay.
Like I know I know
Yeah,
that's
yeah.
how it works out in the end, but it's horrible.
Yep.
Okay, Georgetown.
Go.
It was about 108 minutes.
Right on, 108 minutes.
Yep.
Hold on, I'm writing that down.
All right.
Thanks.
All right. I'll see you tomorrow.
Yeah, we'll see you. We might as well leave this on the Zoom too, right? So units for tau equals, wasn't that tau? Probably, pretty sure. I don't want to have to rederive the different Q. Should probably check it, right? So didn't we say it was something like FB, MG, minus FB equals M dV/dt.
Mhm.
So G minus I LB over M equals dV/dt. And then here, that's G minus B squared L squared V, because there's a BLB, it'll be I, oh, divided by Mr., because there was an R. BLB divided by R, there was a BL. Okay, got it. So we get a Mr. G over B squared L squared. And then we're gonna get a Mr. over B squared L squared dV dt. So what's in the numerator must cancel that t, right? Minus 8. So cross multiplying, I get a dt over. Okay, that was it. Sorry. All right. You want to figure out the units, right?
Yep.
This is kind of a fun exercise. I would call this advanced unit checking. All right, we've got to have some equations that have.
Oh, I see what's going on. You're gonna set, so instead of actually doing the actual specific units of the thing, you set those values in terms of other units, and then those eventually, like, those units should start canceling out.
Right? And just from unit land?
Yeah.
Right?
Yeah.
So this helps because I've got kilograms involved, which I didn't have before, but I don't see any ohms. I need an equation with ohms in it.
I think V equal that.
Okay, let's try it. Well, that says volts. But now you got voltage in there. Crap. I need an equation with voltage in it. It has the same symbols in it somehow. Give me another equation. Induced EMF, what is it?
Wasn't it V times L times like V? Oh, wait, that's not complete.
This is the way to get it. You agree that's one?
Yeah.
Well, help me out. What are the unit, do you remember that flux is something like B times area?
No,
V
but I haven't taken your word for it.
It's BA.
Oh,
BA cosine theta. Remember that? We saw that a lot. Okay. Well, give me the units.
let's see, B,
E is in volts.
yeah.
What are the units of number of turns?
Nothing.
So what are the units of B?
B or Tesla's. It's just a meter squared. And dt time, seconds.
Got it. Do you agree that a Tesla meter squared per second is equal to an amp ohm?
Yes,
Well, do you agree that a Tesla meter squared per second ohm is an amp?
all right,
Do you agree I can plug that into here?
yes.
That's going to be Tesla squared meter cubed. Meter squared over second ohms.
Yes.
So give me the units of a kilogram now. Clean this up and tell me how a kilogram relates to ohms, Teslas, meters, and seconds. Just get rid of that.
Oh, so then 1 meter per so that'd be what, Tesla squared times meter squared. And then. Seconds. So times, okay, times, okay.
So my claim is a kilogram relates to all these other units, ohms and Teslas and meters, using this equation. I claim this must be true because all the other equations we have used have been tested and work, and so these units must also be true.
Okay.
We're almost done. Sorry, Miles. Okay. So when I plug in the units up here, do you agree we have a Tesla squared meters squared second per ohm times an ohm divided by Tesla squared meter squared.
Yes.
What drops out?
That's terrible.
You asked.
And it's horrible.
That's why I didn't do it. But it does work, agreed?
Yeah.
So this is a trick you can do. It's an advanced unit check. And it's not easy, but the trick is just keep pulling equations until you can get the units you want in terms of the units you care about. And the only way you can do it is just by keep pulling equations.
Yeah, it's essentially just like, okay, if you're gonna be deriving, so don't like try to get the more specific, the actual specific variable for like, so like, yeah, amp can be derived further to like cool, for example, that's not gonna help us.
You could do it
Well,
that
you
way
could.
too, and I'd have to think how to do it.
Yeah, but now you need more equations that relate coulombs to other things and stuff like that.
Right.
But, so,
Okay, do you agree we could have done QVB?
yeah,
And that would have had meters per second and Teslas, but charged. Then I would have had to use capacitance.
yeah, and so it would
And then I
have,
could have used tau equals RC.
Mhm.
To relate capacitance, right? This is in seconds. So I see that a farad times an ohm is a second.
Mhm.
So then a farad is equal to what, a second per ohm? You could have gone
Yeah.
that way if you had done QVB. Yeah, it sucks.
yeah,
Can I stop the live stream now? I'm gonna do it. Okay, that was the units. Cool.